Good morning. Since I'm pretty much over the plague or whatever it is I caught in the latter part of last week, I want to make a short video today that concerns some linear algebra facts. This is going to have to do with inverses and a relationship that's going to let us calculate certain quantities in a very easy way. It's going to be convenient for me to write out determinants of matrices. And for our purposes, in view of the way we've been representing things, it's going to be most convenient for me to make up a symbol, capital M, mu nu, for each choice of mu and nu. M mu nu is -1 to the mu plus nu power times the determinant of the matrix that you get when you delete row mu and a column nu from the A matrix. Take each one of these, multiply it by the corresponding number out of the matrix, sum them all up, as with the Einstein summation convention, and this will be the determinant of A. Also, in linear algebra, we found out that the mu nu component of the inverse of A is 1 over the determinant of A times one of these m quantities, except it's not m mu nu, it's m nu mu. I really should have written these indexes upstairs, but since I'm going to change names in a minute, it won't make any difference. When we look at the divergence and Laplacian, it's going to turn out that certain combinations of Christoffel symbols are important to us. In particular, it's going to be important to look at Christoffel with some index alpha, and these two indexes are the same, which means I'm going to figure out all possible Christoffel symbols, alpha, index, same index, and add them up. This is a contraction on the upper and last index below. Using our formula for the Christoffel symbols in terms of the metric, though, I can write out an expression for this summed Christoffel symbol in terms of derivatives of the metric and the components of the metric in the upstairs version. That would be the inverse matrix to the lower stairs version. That last term is interesting to me. I'm going to relabel that last term. What I'm calling mu right now, I'm going to start calling sigma instead, and what I'm calling sigma, I'm going to start calling mu instead. But the metric in either its lower version or its upper version is a symmetric tensor. So here, I change nothing if I swap the sigma and mu, and here, I change nothing if I swap the alpha and the sigma. By doing this, I see that the thing that I'm subtracting away in the third part is the same thing that I was adding in the middle. The second and third terms actually cancel each other out. In what surely must be a candidate for the most atrocious notation so far, we're going to use the letter G to represent the determinant of the metric tensor components in downstairs form, even though G is the name of the tensor itself. This convention is followed only for the metric tensor, and it's up to us to keep the context straight. So this quantity, which I'm claiming will be useful for us, gamma mu alpha mu, turns out to be 1 over 2 times 1 over the determinant of the metric tensor components in lower format times m with the indexes sigma and mu instead of mu and sigma, g mu sigma comma alpha. It's a point worth mentioning that the m numbers typically don't form a symmetric matrix, even though the g's do. So I am not free to swap the sigma and mu here, but I am free to swap the sigma and mu there. I've thought about how to approach the other half of this little calculation several ways. I think the best way to do it is to just be mercenary. I'm going to calculate this quantity. The way people figured this out is they fiddled around with the calculations a whole lot until finally someone noticed that there was a pattern to this. Oh, and also we're still in the context of Euclidean geometry, so the determinant of the metric should be positive. If we're doing special relativity, people will often write negative g under the radical sign to take care of the fact that the determinant of the metric is negative. We'll talk more about that later, though. Doing the chain rule a couple of times, again, we find out that the partial with respect to x alpha of natural log of a radical g is 1/2 1 over g m mu nu g mu nu comma alpha. And this looks very, very similar to the formula that we got for sigma mu alpha mu, which worked out to be 1/2 1 over g m sigma mu g mu sigma comma alpha. The only difference between these two expressions is, in this expression, the indexes here and here are the same, and in this one, they're in the opposite order, sigma mu versus mu sigma. As I said before, even though I'm getting these subdeterminants out of a symmetric matrix, it is not true that m sigma mu and m mu sigma are necessarily the same thing, but it is true that g mu nu and g nu mu are the same thing. So I'm going to interchange the mu and nu because of the symmetry of the metric. I get this equation. I'm going to make some substitutions for indexes. What I'm currently calling mu, I'm now going to start calling sigma, and what I'm calling nu, I'll start calling mu instead. The result is 1/2 1 over g m sigma mu g mu sigma comma alpha. One half 1 over g, 1/2 1 over g, m sigma mu g mu sigma comma alpha, g mu sigma comma alpha. This thing that we just calculated is the same number as gamma mu alpha mu. So the punchline is this. If I need to know these quantities, which I'm going to need shortly, one way to do it would be to sit down, figure out all of the Christoffel symbols, and then make the appropriate sums. That's a perfectly valid way of doing this, but obviously would take a lot of calculating. On the other hand, I could calculate the determinant of the metric, calculate the natural logarithm of that, and then differentiate with respect to x number alpha, and I'll get the same quantities. For example, if I'm in polar coordinates, and I assume that the r is positive, non-negative anyway, so that square root of g is r, then gamma mu alpha mu is the partial derivative with respect to coordinate number alpha of the natural log of radical g natural log of r. If you're looking at gamma mu 1, if you're if you're looking at gamma mu 1 mu, the first coordinate is r. The partial with respect to r of natural log of r is 1 over r. Gamma mu 2 mu is the derivative with respect to the second coordinate, which is theta in this case, of natural log of r, which is 0. So now that we know this fact, if I need to know these quantities, it's very easy to get them. In the next video, we're going to look at how this works in terms of three-dimensional spherical coordinates, still in a Euclidean space, and then we're going to make a discussion of the divergence and the Laplacian, which will involve these quantities, and right then we'll be ready to completely give up on the idea of a globally flat space. Until then, I hope everybody has a good day. I'll talk to you again soon.